Just picture this. Your entire digital world goes completely silent. Your mission-critical cloud servers,
Yeah.
the smart coffee maker brewing your morning cup, suddenly they're just not speaking. What if one tiny, almost invisible screw-up in a cable could instantly crash an entire multi-million-dollar data center?
Wow, yeah.
Or, a forgotten software update on one single device leaves a gaping neon-lit hole in your security. This isn't just about blinking lights and wires. It's really about the silent, intricate language that powers our very modern existence. From the cloud to your coffee maker, everything is connected, and it all starts with data communications.
Before we embark on this truly fascinating exploration into the foundational secrets of our digital world, just take a brief moment to hit that like button, subscribe to the deep dive, and share this with anyone curious about what truly underpins our connected lives.
Yeah, definitely share it. It's the kind of insider knowledge that could genuinely help position you for a bright future in your chosen career, whether that's in business, IT, or, well, beyond. And as always, remember to check the description for access to a wealth of additional resources we've curated, which we think you'll find incredibly valuable. Today, we're embarking on a crucial deep dive into the very core of how data moves not just, through the air, but through the robust, often hidden infrastructure and meticulous documentation that make it all possible. We're drawing our insights from the latest CompTIA network plus Guide to Networks, specifically Chapter 2.1, alongside a stack of other essential industry sources and expert perspectives. This dive is, it's tailor-made for students of BCIS 1347 data communications, or anyone studying information systems, computer networking, or simply aiming to be truly well-informed in today's interconnected landscape.
Exactly. Our mission today is to kind of demystify the physical backbone of our digital world and underscore the absolutely critical, often underestimated importance of documenting every single piece of it.
Yeah.
For those of you in MIS, CIS, IT, or business, understanding these fundamentals is your shortcut to not just grasping what's happening now, but anticipating the future impact and direction of these technologies.
Oh, okay.
We'll be covering essential concepts from your course description, from the fundamentals of telecommunications and data communications technology to the hardware, software, protocols, and those critical managerial issues. By the end, you'll gain crucial insights into identifying transmission technology, explaining media characteristics, understanding network infrastructure, selecting components, designing networks, troubleshooting complex scenarios, and even developing a professional network proposal.
Oh, okay.
We'll highlight how this knowledge directly prepares you for industry-standard network certification exams, providing you with genuinely practical skills.
Okay, let's really unpack this then. When we talk about data communications, I think many people immediately picture Wi-Fi signals, zipping invisibly through the air.
Sure, that's kind
And that's certainly a part of our modern experience. But underneath all that wireless convenience, beneath the floors and behind the walls, there's this tangible, highly organized physical infrastructure that makes those wireless connections even possible.
Exactly.
This is where structured cabling comes in, and it's far more vital than most people realize.
It's true. And, a powerful insight here is that structured cabling isn't just a random collection of wires. It's a standardized, hierarchical approach to designing and installing a cabling infrastructure for communication systems.
Standardized.
Yeah, this isn't about just neatness. It's like a silent guardian for your network. Imagine trying to expand an ad hoc spaghetti mess network. Every new device means tracing a new cable through this tangled web, risking downtime, and introducing potential failures that are just incredibly difficult to diagnose.
Oh, I can picture that mess.
Nightmare. Totally. Structured cabling, often based on a robust star topology design, eliminates that chaos. It means you can confidently plug in a new server or move an entire department, knowing the underlying infrastructure is designed to seamlessly absorb that change.
Right.
It's the fundamental difference between building a house on a strong, pre-engineered foundation versus just stacking bricks on dirt. One will last for decades. The other is, it's a disaster waiting to happen.
Good analogy.
For any aspiring business or IT professional, grasping this structured approach is foundational to building resilient and adaptable systems that scale with business needs.
That makes perfect sense. So structured cabling gives us this organized blueprint. Let's take a virtual tour, maybe follow the data's journey through a typical building or campus.
Good idea.
Think of this as the essential roadmap for any future network design or troubleshooting you might do, whether you're laying out a new office from scratch or just trying to figure out why the internet in the break room isn't working. again.
Yeah, the classic break room issue.
Understanding this flow is a core skill for identifying network infrastructure and designing both logical and physical networks. So our first stop on this tour is the very beginning, the external connection point, the entrance facilities, or EF.
Right, the EF.
Yeah.
This is the precise physical location where the incoming wide area network, typically from an internet service provider, your ISP, connects with your organization's internal network.
Okay.
It's essentially the fortified front door for all external communication entering or leaving your premises. This often involves a secure room or enclosure where external fiber or copper lines transition to internal cabling, acting as that crucial gateway between the global internet and your local systems.
Got it. So right after the EF, we hit a really critical point, the demarcation point, or just demarc. This is more than just a physical location, isn't it?
It's absolutely crucial, and you're right. It's more than just a spot on a wall. The demarc is the precise, often legally defined boundary where the ISP's network responsibilities end and your organization's network responsibilities begin.
The handoff point.
Exactly. Everything beyond this point, including managing the local area network, LAN, or wide area network, WAN interconnection that goes to the rest of your building, falls under your management. This is a vital distinction for service contracts, for compliance, and most importantly, for troubleshooting.
Right.
When a network issue arises, the first question is always, is the problem before or after the demarc? Because that tells you whether to call your ISP or your internal IT team.
Makes troubleshooting much clearer. Okay, so from the demarc, data typically moves into the central nervous system of your local network, what we call the main distribution frame, or MDF.
Yeah, think of the MBF as the central brain, the primary nerve center for your entire building or campus network. Often referred to simply as the equipment room, it's the centralized point of interconnection for the company's LAN or WAN.
Okay.
It houses the main cross-connect and critical network equipment like core routers, switches, sometimes servers, serving as the hub for the entire campus. The term, it can refer to the specialized racks holding the equipment or the room itself.
All right.
It's designed for high-capacity, high-speed traffic, acting as the primary artery from which all other network connections branch.
But for a large campus or a multi-story building, running individual cables from this central MDF to every single workstation, that would be incredibly inefficient and probably exceed distance limits pretty quickly, right?
Oh, absolutely. That's where intermediate distribution frames, or IDFs, come in.
Okay, IDFs.
Precisely. IDFs are like local substations or regional branch offices for your network. They're smaller, localized equipment rooms that provide an intermediate connection between the MDF and end-user equipment, typically located on different floors or in different buildings.
Okay, breaking it down.
Exactly. They help distribute connectivity more efficiently across a larger area, reducing the length of horizontal cable runs and improving overall network performance and reliability. Like MDFs, the term IDF can refer to the racks within the room or the room itself.
Gotcha.
They ensure that data can reach its destination without excessive signal degradation, making the network more scalable and manageable.
So how do all these separate rooms, the EFs, the MDF, and the IDFs, actually connect to each other across a large building or even an entire campus? What's linking them?
That's through vertical cabling, often referred to as backbone cabling.
Backbone, okay.
These are the high-capacity cables, or sometimes wireless links, that provide the essential interconnections between the entrance facility, the MDF, and the IDS. They typically run through risers between floors in a building or underground between different buildings on a campus, forming the core arteries of your network. They carry the bulk of your data traffic at the highest speeds.
So the heavy lifters.
Definitely. They are designed for durability and bandwidth, acting as the superhighways of your network infrastructure.
And from those IDFs, how does it finally get to my desk or the device I'm actually using? That's our horizontal cabling, right?
That's it. This is the final leg of the journey, the cabling that connects individual workstations, IP phones, or wireless access points to the closest data room, specifically to the switches housed there, usually in an IDF. It runs through wireways, conduits, or ceiling spaces, often terminating at a wall jack. It's critically important to remember there's a maximum allowable distance of 100 meters for horizontal cabling, that's 90 meters for the permanent link, plus 10 meters for patch cords to maintain signal integrity and performance.
Right, that 100-meter rule.
Yeah. This cabling can include unshielded twisted pair, UTP, shielded twisted pair, STP, or even fiber optic cables, depending on the specific requirements and desired performance level.
And where does it all end up from the user's perspective,
Yeah.
the work area.
This is the endpoint, your direct interface to the network. It's where the end user equipment, like your computer, printer, or maybe even a smart thermostat, connects to the network via wall jacks or outlets, completing the horizontal cabling system.
Okay.
It's the moment the digital journey becomes physical for the end user, tying into that vast, complex infrastructure we've just described.
So we've navigated the entire physical journey data takes within an organization. For any of you looking to build, manage, or even just troubleshoot a network, whether it's for a small business or a massive data center, truly grasping each of these components, the EF, DMARC, MDF, IDFs, all the cabling, isn't just theoretical knowledge.
Got it all.
It's the foundational roadmap that empowers you to design robust systems and diagnose problems efficiently. It's about being able to visualize the entire digital plumbing of a building before you even pick up a single cable.
Exactly.
This is precisely why your BCIS 1347 course emphasizes identifying network infrastructure and appropriate cables and connectors by name and function. And it's the very first step in applying effective network troubleshooting techniques for any given scenario. Now, beyond just knowing where everything connects, there's the equally critical question of how all this powerful, often heat-generating equipment is physically housed and managed. Because if your servers and switches are just piled on the floor, well, you're not just looking at a mess, you're looking at a major disaster waiting to happen.
Oh, absolutely. A fire hazard, tripping hazard, cooling nightmare. Yeah.
So how do we bring order and safety to this essential hardware?
That's where rack systems come in, and they are far more sophisticated than they might appear at first glance. Racks are essential mounting hardware for network equipment. They're meticulously designed to optimize square footage in equipment rooms where space is always at a premium, and to ensure adequate spacing between devices, easy access for maintenance, and crucially efficient ventilation for these heat-sensitive machines.
Okay.
They can be wall-mounted for smaller setups, ceiling-mounted, freestanding in larger rooms, or even bolted directly to the floor for maximum stability, adapting to the specific needs of the space and the volume of equipment.
And these racks aren't just random sizes, are they? There's a universal standard, which is always helpful in IT.
Absolutely. Standardization is key here. Rack height is highly standardized and measured in racks units, often abbreviated as RU, or simply U.
RU, okay.
One RU is precisely 1.75 inches. This standardization is incredibly practical. A common industry standard for full racks is 42U, which stands about 6 feet tall, while half racks are typically 18U to 22U tall.
2U, got it.
This uniform measurement allows for incredibly efficient planning of equipment placement, maximizing density, and simplifying future expansion. You know exactly what size devices will fit and how many you can install.
So if I'm looking at equipment specs, I'll typically see its height specified in U.
Exactly. And beyond height, racks also have a standard width. Equipment racks typically come in a standard 19-inch frame, meaning the internal mounting width is 19 inches, though 23-inch racks also exist for specialized equipment.
18-inch mostly.
Yeah, mostly. This standardization ensures compatibility with a vast range of network devices from different manufacturers worldwide, from switches to servers to patch panels. Everything just fits together.
With potentially dozens of servers, switches, and other devices in a single rack, managing them would seem to require a separate monitor, keyboard, and mouse for each one.
That sounds like
A logistical nightmare.
it would be an absolute nightmare, yeah, and totally impractical. Thankfully, that's where KVM switches save the day.
KVM, okay.
KVM stands for keyboard, video, and mouse. To manage multiple devices on a rack without needing a dedicated console for each, KVM switches connect several devices to a single monitor, keyboard, and mouse.
Clever.
It provides a central control portal, allowing an administrator to switch between managing different servers or network devices with just a few keystrokes. This saves significant space, reduces cable clutter, and streamlines management, especially in crowded data rooms or, remote management scenarios.
Speaking of crowded data rooms and the amount of heat all this equipment generates, how do they handle it? I've heard about hot aisle-cold aisle layouts, which sounds kind of intriguing.
It is intriguing, and it's a brilliant engineering solution to a very practical, very serious problem. In larger data centers with multiple rows of racks, a specific layout is used to manage heat efficiently and economically.
Yeah.
This is the hot aisle, cold aisle configuration.
Okay, explain that.
Imagine 2 rows of racks facing each other, forming a cold aisle between them. Cool air is actively pulled from floor vents or low-lying wall vents into this cold aisle where the fronts of the equipment face.
Right.
The equipment then draws in this cool air to operate. The exhaust, which is hot, is directed into the hot aisles created at the backs of the racks, away from the equipment fronts.
Ah, separation.
Exactly. This heated exhaust air is then efficiently directed into exhaust vents for cooling, maximizing cooling efficiency and preventing the hot air from recirculating and preheating the incoming cool air. It's a highly optimized critical system for maintaining stable operating temperatures.
That hot aisle-cold aisle design is a brilliant solution. So with that kind of precision and airflow, I imagine the exact placement of equipment within those racks, especially switches with their different intake and exhaust ports, becomes absolutely paramount, doesn't it?
Precisely. Network switches, for example, are designed with specific airflow patterns, and misplacing them can disrupt the entire cooling strategy. Portside intake switches are engineered to draw cool air from the cold aisle, typically through the front of the rack where their data ports are located. Conversely, portside exhaust switches are designed to face the hot aisle, expelling warm air through their port side. Proper placement of these switches within the hot aisle-cold aisle layout is crucial for effective cooling, preventing equipment overheating, which, can lead to performance degradation, increased energy consumption, and even catastrophic device failure.
Right.
It's a detail that can make or break the entire data center's efficiency.
Okay, that's a lot of highly structured detail to visualize. So maybe let's use that analogy you hinted at to tie this together. Think of a modern data center equipped with structured cabling and rack systems as what? A highly optimized high-tech city.
That's a great way to think about it, yeah. The entrance facilities are like the main international airport, bringing in all external traffic. The DMARC is the customs checkpoint defining responsibility. The MDF is the central power station and main railway hub connecting major districts. The IDFs are like local substations or train stations, distributing power and connectivity to individual neighborhoods or skyscrapers.
Okay.
The cables themselves are the intricate network of roads and highways, from the multi-lane backbone routes to the local streets that reach every building. And the racks.
The skyscrapers.
Exactly. They're the carefully designed, climate-controlled skyscrapers housing your essential network residents, your devices and servers. Every part has a purpose, everything is meticulously planned, and the climate is rigorously controlled to keep the city running smoothly.
I like that. And the practical takeaway here is that understanding rack systems, their standardized measurements, RU 19-inch width, and the environmental controls like hot aisle, cold aisle, isn't just theoretical knowledge for an exam, right?
Not at all. It's a fundamental part of identifying network infrastructure. It's a key step in selecting appropriate wired, wireless, and optical fiber networking components for a given set of requirements, ensuring optimal performance, longevity, and energy efficiency for the entire system. Without this knowledge, you're essentially trying to build a city without knowing how to construct its buildings or manage its climate, a recipe for disaster and unsustainable growth. This knowledge directly helps students design logical and physical networks that are both robust and efficient.
So we've talked about the architecture of the network, the rooms, the frames, the racks, forming the skeleton of our digital city. Now let's get down to the actual pathways for data, the cables themselves.
The roads and highways.
Exactly. You've got options here. And choosing the right one can truly make or break your network's performance, cost efficiency, and future-proofing capabilities.
Absolutely. And a critical aspect here is the continuous evolution of transmission media. While traditional copper cables still play a significant role in many networks today, especially for shorter runs to individual workstations, the increasing, almost insatiable demand for blistering speeds, massive capacity, and superior performance means that fiber optics are becoming an indispensable and often preferred option.
Fiber's really taking over in some areas.
It really is. This is particularly true in modern data centers, for campus backbones, and for connecting high bandwidth devices. For students in data communications, understanding these alternatives and their nuances is absolutely critical for making informed design and implementation decisions that will stand the test of time.
Let's start with the familiar, the workhorse of many networks, copper cabling.
Okay. Copper cabling encompasses types like unshielded twisted pair, UTP, and shielded twisted pair, STP, which are commonly categorized by performance levels such as Cat 5, Cat 5e, Cat 6, Cat 6a, and even Cat 7 or Cat 8 now.
Right, the CAT ratings.
Yeah. These cables are robust, relatively inexpensive, and widely used for horizontal cabling, connecting workstations to switches. However, copper does have inherent limitations. Its maximum effective distance is typically around 90 meters for permanent links, with that additional 10 meters allowance for patch cords at each end.
That 100-meter total again.
Exactly. More critically, copper struggles with electromagnetic interference, EMI, and signal degradation over longer distances or at higher frequencies, meaning it has less future support for extremely high-speed systems, think 40 Gbps and beyond, compared to fiber.
Okay.
For example, while Cat6 can handle 10 gigabit Ethernet, it only does so reliably up to about 55 meters, whereas Cat6 Array extends that to 100 meters. So there are nuances even within copy.
Got it. And then there's the high-speed champion, the true powerhouse, fiber optic cabling.
Ah, yes, fiber. Optical fiber cables offer significant, often game-changing benefits over copper. We're talking fast speed, incredibly high capacity, and high-performance data transmission.
How fast are we talking?
Well, to give you a surprising fact, a single strand of fiber can theoretically carry terabits of data per second, enough for millions of simultaneous phone calls or thousands of 4K video streams over distances far, far exceeding copper.
Wow, terabits.
Yeah. They can also provide up to 60% space saving over copper UTP cabling in trunking or backbone applications, which is a huge advantage in dense data centers where conduit space is precious.
Space saving is big.
Huge. We categorize them into types like OS2 single-mode fiber, which is ideal for very long distances like campus-wide links between buildings, and OM1, OM2, OM3, OM4, and OM5 multi-mode fiber, suitable for shorter, high-bandwidth runs within a building or data center, such as connecting racks.
Single mode, multi-mode.
Right. And emerging MTP-MPO cables offer even higher densities for data center environments. Fiber is increasingly becoming not just a non-negligible option, but often the preferred choice for data center cabling due to its distinct benefits in work performance, offering superior resistance to EMI and significantly greater bandwidth over distance.
Okay. And what about powering devices over these cables? Power over Ethernet, PoE, has become so common for things like IP cameras, VoIP phones, wireless access points. How do our cable choices impact that?
That's a critical point for network design and often overlooked. PoE isn't just a simple power tap, it's actually governed by evolving standards like 802.3AF, original PoE up to about 15 watts, 802.3S PoE plus sour up to 30 watts, and 802.3BT PoE plus plus or 4P PoE up to 90 watts, each delivering progressively more power.
So the standards matter.
Absolutely. So while Cat5 or Cat6 might effectively power a basic IP phone or small wireless access point up to their 90-meter limit, you'd absolutely need Cat6A, with its superior ability to handle heat and lower resistance, for power-hungry devices like high-resolution PTZ security cameras, digital signage, or even thin clients, especially as you approach that 90-meter distance.
So Cat6A for higher power needs.
Definitely preferable, yeah. Choosing the wrong cable here isn't just about speed, it's about whether your device even turns on reliably, whether it throttles performance, or if the cable itself becomes a potential fire hazard due to excessive heat generation from the current.
Yikes.
This directly addresses your course's focus on alternatives available in hardware and transmission facilities, helping you explain the makeup of various transmission media and their associated characteristics, enabling you to select appropriate wired, wireless, and optical fiber networking components for a given set of requirements.
So just having the right cables isn't enough then. How you install and manage them is paramount. Like you said, precision matters, because a tiny error during installation can lead to massive headaches and costly downtime later on.
This raises an incredibly important question. How do we avoid unnecessary loss, performance degradation, and, well, catastrophic problems during deployment? Even with the distinct benefits of fiber, improper practices can severely impact data transmission and lead to costly downtime. Adhering to best practices is essential for both immediate functionality and long-term network health, reliability, and troubleshooting. These are the details that separate a robust, stable network from one that's a constant source of frustration.
So let's dive into some of these crucial best practices for installation and management. What's the first thing we need to be aware of, especially with fiber? It seems more delicate.
It is. First, with fiber, you must always pay attention to the fiber bend radius. Fiber optic cables, while incredibly powerful, are also delicate. Never bend fiber patch cables beyond their specified minimum bend radius, which is typically, a few centimeters depending on the cable.
Okay, don't kink it.
Exactly. Too sharp a bend can weaken the data signal flow by causing light to leak out, or it can even physically break the hair-thin fiber strands, leading to significant data transmission issues, intermittent connectivity, or complete network outages. It's like kinking a garden hose. The water flow is severely restricted.
That makes perfect sense. What else should we watch out for, especially with those delicate fiber connections?
And face contamination is another silent killer for fiber optic connections. You might think, oh, it's just a tiny speck of dust. But remember, light is traveling down a hair-thin glass strand.
Microscopic level.
Right. Even a microscopic particle of dust, a tiny oil smudge from a finger, or debris on the end face of a fiber optic connector can scatter that light, weakening the signal to the point of failure. It's like trying to shine a flashlight through a dirty window, you lose most of the light.
Wow.
These are one of the most common causes of network failure. So always check the condition of the end, face carefully with a microscope, and clean them properly with specialized tools before connecting them to avoid network havoc. This prevents hours of frustrating troubleshooting trying to find an invisible fault.
Good tip. And what about mixing copper and fiber in the same pathways? Any concerns there?
There definitely are, which is why it's generally best practice to ensure separation of cable runs. Keep copper and fiber cable runs separated whenever possible. Copper cables are much heavier and, if laid on top, can physically damage delicate fiber optic cables.
Ah, the weight.
Yeah, and moreover, copper cables generate electromagnetic interference, or EMI, which, while not directly affecting the light and fiber, can interfere with adjacent copper cables or sensitive network equipment. Maintaining separation helps prevent both physical damage and signal integrity problems.
EMI is a big deal, isn't it? It feels like an invisible enemy sometimes.
Absolutely, especially for copper cabling. Avoiding EMI sources is critical. You should always install copper cables at least 3 feet, about a meter, away from things like fluorescent lights, power cords, building electrical cables, fire prevention components, power lines, TVs, copiers, electric motors.
Lots of sources.
Lots. These are all common sources of EMI that can cause a range of problems, from intermittent data errors and slow network speeds to complete, frustratingly intermittent connectivity issues that are incredibly difficult to diagnose because they seem to come and go.
Right. I've also heard about leaving too much twisted pair exposed when terminating Ethernet cables. Why is that such a big deal?
Yes. When you're terminating twisted pair cabling, putting that RJ45 connector on the end of a Cat5e, Cat6, or Cat6a cable, this is a really common yet critical mistake. Exposing too much of the twisted pair before the termination point.
How much is too much?
You really want to keep the twists going as close to the termination point as possible. Exposing more than about half an inch, maybe an inch at the absolute max, increases crosstalk.
Cross-leg, okay.
Yeah, imagine your data signals are whispers in a crowded room. If you untwist those wires too much, those whispers start bleeding into each other. It's like trying to have a clear conversation when someone else is talking right over you. Even that tiny bit of exposed, untwisted wire can introduce enough interference to cause intermittent data errors, slow your network down, and create a troubleshooting nightmare.
Got it. Keep those twists tight. And once it's all installed, before you flip the switch and go live, how do you know it actually works reliably?
You absolutely must always perform continuity testing. Before deploying any installed cable and bringing your network live, use a specialized cable tester.
Cable tester, right?
Yeah, these tools ensure it transmits data reliably, that all wires are connected correctly in the right order, no split pairs, and there are no shorts or opens. This critical step prevents you from searching for errors later in an active network, which can be far more time-consuming, disruptive, and costly when users are relying on the service.
Test first, deploy second.
Always. A few minutes of testing up front can save days of troubleshooting later.
What about organizing cables? We see those neat bundles in data centers, but can you go too far with, say, cable ties?
Yes, you definitely can. While organizing cables with ties, like Velcro straps, which are often preferred over zip ties, is excellent for management and aesthetics, you must ensure they are not too tightly secured.
Loosely cinched.
Exactly. Over-tightening, especially with plastic zip ties, can squeeze the outer covering of the cables, subtly changing their electrical characteristics, causing data errors, and making troubleshooting challenging because you might not immediately identify the physical stress point. They should be snug enough to hold the bundle, but loose enough to allow some movement and not deform the cable's jacket.
And for protecting the cables themselves from physical damage or environmental factors, what should we use?
Use appropriate cable coverings and conduits to protect cables from physical damage, pests, maybe even moisture. Plenum cabling, for instance, is a specific type of cable with a fire-resistant jacket.
Plenum rated.
Right. It's designed for use in plenum spaces, those air-handling ducts and ceilings, to reduce smoke and flame spread in case of fire. This is a critical safety consideration in commercial buildings, as non-plenum cables can produce toxic smoke and help spread fire rapidly through air ducts. Using the right type is often a building code requirement.
Safety is paramount. And that brings up the concept of grounding, too. How important is that?
Indeed. Proper grounding of all network equipment and cabling infrastructure is absolutely essential. It's not just for preventing electrical interference and signal noise, but primarily to ensure safety by providing a safe path for stray electrical currents, protecting both equipment and personnel from electrical hazards like surges or faults. It's a fundamental electrical safety practice applied directly to your network.
Future changes, upgrades, moves. They always happen. How do we account for that flexibility during the initial installation? Seems tricky.
You build it in. You should always maintain some slack in cable runs. Don't cut cables to their exact taut length. Building in a little extra slack, sometimes called a service loop, accommodates future changes, moves, adds, or simply allows for rerouting without having to replace entire cable segments.
All right.
It also prevents strain on connectors and equipment ports, which can lead to premature failure over time.
For managing truly large bundles of cables, especially in equipment rooms, what tools are indispensable for clear routing? Looks chaotic otherwise.
It can be. Cable trays and raceways are vital management assemblies. These structured systems, often metal or plastic channels, provide clearly defined routing paths for bundles of cables, reducing congestion in termination panels and equipment racks.
Keeps it organized.
Very organized. They make cabling much easier to follow, identify, and validate during installation, maintenance, and troubleshooting, significantly improving organization and reducing the likelihood of accidental disconnections or damage.
And for making sense of all those individual connections in the equipment room without having to plug and unplug directly into expensive switches all the time.
That's where patch panels come in. These are passive devices, basically just rows of ports used to organize and connect lines. They provide immense flexibility for network configurations and simplify troubleshooting by creating a central, easily identifiable, and modular point for all horizontal cable runs to terminate.
So the permanent cable goes to the patch panel.
Exactly. Instead of plugging a desktop's wall jack cable directly into an expensive switch port, the cable terminates at a patch panel, and then a short, easily replaceable patch cord connects the panel port to the switch port. This protects the expensive switch ports from wear and tear and makes changes far easier and less risky.
Brilliant. Finally, what's the one thing that helps you find anything and everything in that potential sea of cables? It seems so basic, but so important.
Labeling, again, is paramount. It cannot be stressed enough. Every single cable, port, and jack should be clearly labeled with from and to locations, for example. IDF2, rack 3, port 12, going to work area 4B, jack 1.
Detail labels.
Yes. This makes installation, moves, adds, and changes much easier, safer, and far more efficient. Color coding cables for different purposes, maybe yellow for data, blue for phone, red for critical uplinks, can also significantly enhance clarity and reduce human error, especially in an emergency situation.
These best practices directly contribute to students' ability to identify appropriate cables and connectors by name and function, select wired, wireless, optical fiber components, develop physical designs, and configure network connections effectively. Ignoring these details, well, it can lead to significant real-world business problems and massive headaches down the line.
Absolutely. It's the difference between a network that works reliably, efficiently, and safely, and one that's constantly failing, costing money and productivity. It's professional versus amateur hour, basically.
Right. It's not just about the quality of the connections themselves or how they're installed. It's also about the environment those connections live in. We're talking about protecting your network from heat, humidity, unauthorized access, literally the physical elements that could bring down your entire operation, regardless of how perfectly the cables were laid.
This raises a really important question. How do organizations protect their sensitive, often mission-critical network equipment from both environmental threats and security breaches simultaneously? It's a multifaceted challenge that requires dedicated systems, continuous monitoring, and constant vigilance. The physical environment is the absolute first line of defense for your most valuable digital assets.
So let's start with the most obvious and relentless environmental threat in a data room.
Heat.
How are these vital spaces kept cool, especially with racks full of heat-generating servers? Standard AC won't cut it, right?
Definitely not. Data rooms house heat-sensitive servers and network devices that continuously generate a significant amount of heat. Because of this, they almost always have dedicated HVAC, heating, ventilation, and air conditioning systems.
Dedicated HVAC.
Yeah, these aren't just your typical office AC units. They are precision cooling systems, often managed separately from the rest of the building's climate control. Their sole purpose is to maintain optimal cooling, humidity, and air circulation, preventing overheating, which can lead to equipment failure, reduced lifespan, and severe performance degradation. They are mission-critical infrastructure themselves, not just for comfort.
I can imagine those advanced HVAC systems are pretty smart themselves. Are they networked and automated? It seems like they'd have to be.
Absolutely. The HVAC sensors within data rooms monitoring temperature, humidity, airflow, maybe even smoke, are often network devices themselves. These sensors, along with their control software, are prime examples of an industrial control system, ICS.
ICS, okay.
An ICS acquires real-time data from a physical system, like the ambient temperature in a server rack, and then either manages it automatically by adjusting the cooling units or presents that data to humans for continuous monitoring and manual intervention. They're designed for reliability and often operate on separate, hardened networks to prevent cybersecurity compromises.
And there's an even more complex, large-scale version of that, right? SCADA, I've heard that term.
Yes, exactly. A more complex and widespread type of ICS is SCADA, supervisory control and data acquisition. SCADA provides a comprehensive interface for widespread control systems, allowing operators to monitor and manage large-scale, geographically dispersed infrastructures.
Like what?
SCADA systems can oversee and control everything from electric utilities and water treatment plants to manufacturing equipment and traffic signals. In a data center context, a SCADA system might oversee the entire environmental control infrastructure, integrating HVAC, power distribution units, PDUs, uninterruptible power supplies, UPS, and even building lighting and entry systems into a single, centralized management platform. It offers a bird's-eye view and granular control over critical physical operations.
Wow. Okay, so all these sensors, controls, and computing systems that manage the physical world of the data room, keeping everything stable and secure, what's the collective term for them is the one?
Yeah, the sensors, controls, and computing systems that manage ICFs and SCADA systems are collectively known as operational technology, OT.
Oh, okay.
This hardware and software directly interacts with physical infrastructure to monitor and control industrial processes and physical systems, ensuring the physical environment of your network is stable and secure. This is distinct from traditional IT, which manages data, but it's becoming increasingly interconnected. Understanding the unique security challenges of OT is a rapidly growing field, especially as these systems become more networked and vulnerable to cyber threats.
That makes sense. Beyond environmental control, what's paramount for keeping the actual machines safe from physical intruders or unauthorized personnel? Locks and cameras.
Physical security is absolutely paramount and often overlooked until it's too late. Every data room should be secured behind multiple layers of locked doors with access limited to only essential authorized IT personnel.
Multiple layers.
Yes, this means strict key card management, maybe biometric systems like fingerprint or facial recognition or multi-factor access codes. Furthermore, implementing security cameras to monitor data room entrances, internal aisles, or access points leading to the area is a common and critical preventative measure. This provides an audit trail for who entered when, and acts as a significant deterrent against both insider threats and external breaches.
The relevance here is undeniable. Protecting your physical infrastructure, from controlling the climate to restricting access, is the foundational layer of defense for any robust network. Failing here can render all your advanced cybersecurity measures moot.
Completely useless. Yeah.
You can have the best firewalls, the most sophisticated intrusion detection systems in the world, but if someone can simply walk in, unplug your servers, or you pour a cup of coffee on a switch, all that digital protection is worthless.
Gone. Instantly.
It highlights why your course focuses on formulating a risk assessment and developing an appropriate security strategy to mitigate risks for a given set of requirements. Physical security is step one. We've built this incredible physical network with meticulous cabling and climate-controlled racks. But, I've heard horror stories from IT professionals walking into new jobs, inheriting a network that's basically a black box. No one knows how anything is connected or why. How much of a problem is this really? And what's the fundamental solution to avoiding that kind of disaster?
That's an excellent question, and it's a far more pervasive and critical issue than many organizations realize. The fundamental solution, the often unsung hero of network management, is documentation.
Documentation. Okay.
We connect this to the bigger picture. Many organizations tragically neglect this crucial aspect. A study by Gartner, for instance, revealed that almost 40% of network outages actually result from human errors.
40%. Wow.
Yeah, and a significant portion of these are directly due to inadequate or outdated documentation. This highlights the absolutely critical role documentation plays in maintaining a stable, reliable, and secure network infrastructure. It's not just a nice to have, it's a foundational pillar for operational excellence, preventing countless managerial headaches and costly downtime.
So, beyond just preventing outages, what are the other big tangible benefits that make documentation so non-negotiable? Why should businesses really care?
Well, comprehensive and accurate documentation offers several profound layers of benefits. Firstly, it leads to enhanced network stability and security. With accurate configurations, network diagrams, and procedures meticulously documented, you prevent outages caused by configuration errors, minimize unauthorized access by clearly defining security policies, and proactively protect against cyber threats by having a clear understanding of your attack surface. Proper documentation helps identify potential security vulnerabilities, allowing IT teams to take proactive measures to mitigate risks before they're exploited, moving from reactive firefighting to proactive prevention. Secondly, it ensures efficient resource utilization and significantly faster troubleshooting. Knowing exactly what hardware and software you have, how it's configured, and where it's located optimizes resource allocation for improved performance and prevents redundant purchases.
Saves money.
Definitely. More critically, when issues inevitably arise, it makes identifying and resolving network problems much quicker and more streamlined, significantly reducing your mean time to repair, or MTTR. You don't have to spend hours trying to reverse engineer a problem or trace a mystery cable. The answer is readily available, saving immense time, money, and frustration.
Makes sense. What else?
Thirdly, documentation facilitates streamlined management and planning. Comprehensive records make it infinitely easier to plan and execute network changes efficiently, whether it's adding new devices, upgrading software, or expanding the network to a new location. It also helps in effective capacity planning, ensuring you don't over-provision or under-provision resources.
Strategic planning support.
Exactly. It's about making informed, strategic decisions. Fourth, and this is massive, it enables effective collaboration and knowledge transfer. When multiple IT professionals work on a network, clear, standardized documentation ensures seamless collaboration, avoids confusion, and prevents conflicting changes that can destabilize the network.
Prevents stepping on toes.
Precisely. It also smoothes the onboarding process for new employees, bringing them up to speed much faster, and critically ensures vital knowledge transfer when experienced IT personnel leave the organization, preventing a devastating brain drain and maintaining institutional knowledge.
That's huge. And
Sure. Finally, it's absolutely essential for compliance and auditing. In today's regulatory landscape, well-documented networks make it much easier to meet stringent regulatory compliance requirements like HIPAA, GDPR, or CCPA, and to effortlessly pass external audits. This ensures the security and integrity of your network and helps your organization avoid crippling legal complications, fines, and reputational damage.
So documentation really is the unsung hero. For anyone studying information systems, or really any business student, understanding documentation isn't just about passing an exam, it's a critical managerial skill. Because when you're making strategic decisions about IT infrastructure, or even just trying to keep the lights on, having robust, up-to-date documentation directly impacts your operational efficiency, your budget, and ultimately your organization's resilience.
Couldn't agree more. It highlights the immense value of preparing students for industry-standard network certification exams, which often emphasize thorough documentation as a cornerstone of good practice.
So you're convinced documentation is vital, and you should be. But what kind of information should actually be included in this comprehensive record? It's clearly more than just a simple list of devices, isn't it, what goes in it?
Absolutely. The scope of network documentation is incredibly broad and needs to be multifaceted. It needs to cover everything from high-level visual representations to detailed operational specifics and even critical contractual agreements. It needs to be a living, breathing, easily accessible repository of all network knowledge serving different stakeholders.
Let's start with the visual side, network diagrams. These seem like a fundamental starting point, right? A picture's worth 1,000 words.
They truly are. Network diagrams are graphical representations of a network's devices and their connections, and they are indispensable for quickly grasping the overall structure and flow. We usually differentiate between two main types: logical diagrams. These illustrate the logical topology of the network. They show things like IP address pools and reserves, the names of major network devices like specific routers, core switches, firewalls, and the types of transmission media used, fiber, copper, etc. They focus on how data logically flows, maybe showing VLANs or subnets.
How it works conceptually.
Exactly. Then there are physical diagrams. These illustrate the actual physical layout, This could be a floor plan showing where equipment rooms are, where cables enter, or more granularly, a detailed rack diagram showing devices stacked to scale within an equipment rack.
The rack diagram seems super useful.
Oh, rack diagrams are particularly crucial for planning equipment installations, troubleshooting physical connectivity, and managing power and cooling, helping you visualize exactly where each component is in the real world.
And are there standard symbols for these diagrams? I feel like I've seen consistent ones.
Yes, thankfully. Cisco systems long ago set the widely accepted standard for diagram symbols representing routers, switches, firewalls, servers, and other network devices. These symbols are universally understood in the networking field, making diagrams comprehensible regardless of who created them. It's a common visual language.
That helps. How do you even begin to map out a complex network to create these diagrams from scratch? It sounds kind of daunting.
It can be. That's where network mapping tools come in handy. Utilities like Nmap, Network Mapper, or its graphical user interface version ZenMat assist significantly in discovering and identifying devices on a network.
In map, okay.
Yeah, they can scan a network segment and tell you what devices are active, what operating systems they're running, what ports are open, and even try to infer the topology. This provides the raw data needed to construct these diagrams, and more advanced tools can even generate visual maps automatically, saving countless hours.
Okay, so beyond visual diagrams, what about the day-to-day operational details, the nuts and bolts of how the network actually runs?
That falls under operating procedures. This essential documentation covers the logical and physical connections on the network, detailed inventory management records, IP address utilization schemes, who has what IP for how long, static versus dynamic, vendor information, support contracts, contact numbers, and internal policies and standards, like how to configure a new switch according to company policy.
Where do you keep all this?
This information should ideally be organized into a searchable database, a specialized documentation tool, or maybe a well-maintained wiki, making it easy for anyone on the team to find what they need quickly and consistently.
You mentioned inventory management. That sounds like an exhaustive amount of detail to track. Is it really necessary?
It is, but it's absolutely vital for asset lifecycle management and security. Inventory management involves monitoring and maintaining all the assets that constitute a network, from tiny patch cables to multi-million-dollar core routers.
Everything.
Ideally, yes. This includes meticulous details for both hardware and software. For hardware details, you track configuration files, model numbers, serial numbers for warranty and tracking, the physical location on the network, and technical support contact information for each device.
Okay.
For software details, you'd note version numbers, vendors, licensing information, crucial for compliance and audits, and technical support contacts. The benefits are immense. It provides administrators with crucial information about network components, helps track costs and benefits, tracks updates to prevent security vulnerabilities, and allows you to anticipate future software needs and plan upgrades.
Sounds like a lot to do manually.
It is.
Yeah.
That's why tools like IT Asset Tool or integrated RMM platforms can automate much of this process, continuously scanning and updating your inventory.
And to keep all this inventory and all these connections manageable, I assume systematic naming and clear identifiers are incredibly important. Otherwise, it's just chaos.
Crucially important. Labeling and naming conventions are not optional. They are essential. Systematic procedures are critical for tracking devices efficiently and reducing human error.
Any tips for good naming?
Yeah, for naming tips, use descriptive but concise names, like FWDC1, EdgeE01 for Firewall, Data Center 1, Edge Device 1. Adhere to any existing employer conventions for consistency. Think from big picture to details in your naming hierarchy, and always consider any security risks from including overly detailed information in names that might be visible.
Good point. And labeling tips.
For labeling tips, use color-coded cables for different general purposes, like we mentioned, yellow for data, red for backbone. Label all ports and jacks that cables connect to with destination and source, and if labels don't fit directly on devices, draw simple diagrams indicating the purpose of each port, slot, and connector, attaching it nearby. Clarity is key.
Finally, what about the broader business context? Network professionals aren't just technical wizards. They operate within a business framework, right? They deal with contracts and proposals.
Absolutely. Network technicians and managers will frequently encounter a variety of business documents that define responsibilities, applications, expenses, and service expectations. Understanding these is vital for effective project management and vendor relations.
Like what?
These include An RFP, request for proposal, which is a formal document used to solicit proposals from potential vendors for a project or service. It outlines the project's requirements, scope, and desired outcomes. An MOU, Memorandum of Understanding, often a non-legally binding agreement between two or more parties outlining their intentions to work together. It's kind of a precursor to a more formal contract.
Okay.
An MSA, Master Service Agreement, which is a foundational contract that defines general terms for future agreements between parties, streamlining subsequent negotiations for specific projects under its umbrella. A SOW, Statement of Work, a formal document outlining the specific work to be performed by a vendor or service provider for a particular project, including deliverables, timelines, and costs. Very detailed.
And the big one, the SLA.
And the SLA, Service Level Agreement, yes. A critical contract defining the level of service expected from a vendor or internal IT department, specifying metrics like uptime guarantees, responsibilities, and sometimes even penalties for non-compliance.
Understanding all these essential documentation types directly supports students' ability to identify network infrastructure, design logical and physical networks, and develop a professional network proposal to address a business problem, ensuring it's comprehensive and clear. It's about building a complete, transparent picture of your network and its strategic implications for the business.
Exactly. It connects the technical details to the business reality.
It's one thing to create documentation. It's another entirely to keep it useful, accurate, and relevant. A stale document is just as bad as no documentation at all, maybe worse, because it can actively mislead you. How do we ensure it remains a living, breathing, and accurate reflection of our constantly evolving network?
That's the million-dollar question, isn't it? How do we maintain consistency and accuracy in network documentation, given that networks are dynamic, constantly evolving entities? The challenge is to make documentation an ongoing, integrated process, not a one-time event that gathers dust. It needs to be treated as a critical network asset itself.
So where do we start with keeping it consistent and coherent across the team and over time?
You absolutely need a standardized format and templates. Define a consistent format for all your documentation using clear headings, bullet points, tables, a logical flow. Create standardized templates for network diagrams, device configurations, IP address schemes, even incident reports.
Templates help a lot.
They ensure uniformity across all records, making it easier for anyone on the team to read, understand, and contribute, regardless of who created the original document. Consistency is key.
And what about when changes are made to the network, which happens constantly, right?
Yeah.
How do you capture those?
You must document network configurations and changes immediately. This is non-negotiable. Accurately document all network configurations, IPs, VLANs, routing rules, firewall settings as they are implemented. Crucially, document any changes made to the network, who made them, why they were made, what devices were affected, the configuration items or CIs, and a precise timestamp.
Immediately.
Not later, right away. This maintains absolute visibility and is absolutely vital for troubleshooting when something inevitably goes wrong. If it's not documented right away, it essentially didn't happen for the purposes of historical record, and you'll be lost trying to figure out what changed weeks or months later.
Manually tracking all that, especially in a large or rapidly changing environment, sounds incredibly time-consuming and, frankly, prone to human error. People forget.
It definitely can be. That's why you should look to automate documentation processes wherever possible. Manual documentation is indeed time-consuming, prone to error, and quickly becomes outdated.
What kind of tools help?
Utilize network documentation tools like NetBrain, SolarWinds, or even configuration management tools like Ansible or Puppet, which can help document state. These tools can automate discovering, mapping, and documenting devices, configurations, and connections across your network. This ensures real-time accuracy, significantly reduces manual effort, and saves valuable time.
Okay, automation is key. But even with automation, the network changes, systems are upgraded, devices are replaced. How often should we actively check the documentation to make sure it's still accurate?
You need to schedule regular review and updates. Don't just set it and forget it. Set aside regular intervals, maybe weekly for highly dynamic elements like IP assignments, monthly for configurations, or quarterly semi-annually for overall architecture reviews to actively review and validate your documentation against the live network.
Build it into the schedule.
Exactly. Keep track of hardware and software changes, document new devices as they're added, and, importantly, remove outdated information. This ensures the documentation consistently reflects the current state of the network, preventing it from becoming a source of misinformation.
And what about consistency in how things are named throughout the network? We touched on naming conventions earlier.
Consistency in naming conventions is paramount. Apply consistent naming conventions for devices, interfaces, VLANs, virtual machines, everything, across your entire infrastructure. This streamlines documentation, improves clarity, and makes it far easier to identify specific elements within your infrastructure at a glance, like using SWBLDG1 FLR3-01 for a switch. It tells you exactly what and where it is. It removes ambiguity.
Got it. This all sounds like highly sensitive information: IP addresses, configurations, physical layouts. How do we keep the documentation itself secure?
Excellent point. Given the extremely sensitive nature of network information, which could be gold for an attacker, it's absolutely crucial to ensure the security of documentation. It must be kept secure and accessible only to authorized personnel, based on the principle of least privilege. Encrypting documentation files, storing them on secure servers with strict access controls, implementing multi-factor authentication for access, and regularly auditing who has access are vital preventative measures against unauthorized access, data breaches, and potential security compromises. This isn't just about keeping it organized, it's about keeping your organization safe.
Adhering to these best practices for network documentation, configurations, and updates prepares students for industry-standard network certification exams by emphasizing a disciplined, professional approach to network management. It's about instilling a culture of thoroughness and foresight, which directly translates to a more stable, secure, and efficient network.
It really does. It's a hallmark of a well-run IT operation.
Okay, so documentation is vital, but no network is infallible. Devices fail, systems go down. It's just an inevitable reality we all face in the digital world, right?
Unfortunately, yes, entropy always wins eventually.
So smart network management isn't just about fixing things after they break. It's about anticipating when they might break and building a system that can gracefully withstand it. How do we do that?
This is where metrics and design principles become strategic, shifting from reactive firefighting to proactive resilience building. We need to understand not just if something will fail, but when we can reasonably expect it to, and, crucially, how quickly we can recover from that failure. This forward-looking approach is what builds genuine resilience into a network.
Okay, so what are the key metrics we use to quantify and anticipate these failures? You mentioned MTTR earlier.
Right. Two key ones are MTBF and MTTR. The first is MTBF, or mean time between failure. This metric represents the average amount of time expected to pass before a device, or a device exactly like it, fails again.
The average time between failures.
Exactly. It's a statistical measure, often provided by manufacturers, that helps you predict the reliability of components and plan for their eventual replacement or maintenance cycles. For example, if a hard drive has an MTBF of 1.2 million hours, it doesn't mean your drive will last that long, but it gives you a probability of failure within a certain time frame across a large number of drives. It helps drive purchasing decisions and maintenance schedules. Then there's MTTR, or mean time to repair. This measures the average amount of time required to repair a failed device and restore it to service, from the moment of failure detection to full operational status.
How long it takes to fix it.
Exactly. A low MTTR is absolutely critical for minimizing downtime and ensuring business continuity. It shows how quickly and efficiently your team can respond and resolve issues. If your MTTR is consistently high, it points to problems in your troubleshooting process, maybe poor documentation or not having the right spare parts readily available.
That focus on MTBF and MTTR makes perfect sense in a world where downtime costs can be astronomical. It means we have to design networks not just for what works, but also plan for what fails. So how do engineers actually build in that resilience, that ability to absorb a failure without the whole system collapsing?
This is where the concept of redundancy becomes paramount. To protect against faults and failures, networks are meticulously designed with redundancy. This means having two or more identical items, services, or connections filling the same role on the network.
Duplicates.
Essentially, yes. If one fails, the other immediately takes over, often without any perceptible interruption to service, effectively eliminating any single points of failure, SBIF, that could otherwise bring down the entire system.
Examples.
Think of it like having dual power supplies in a critical server, or two separate internet connections from different ISPs coming into your building, or maybe duplicate core switches running in parallel. If one path or component fails, there's always an alternative ready to take over almost instantly.
And speaking of having spares, I've heard the terms hot spare and cold spare. What's the practical difference for network uptime? Seems important.
That's a great and very important distinction for understanding recovery times and cost. A hot spare is a duplicate component that is already installed in a device, powered on, and actively synchronized or ready to immediately assume the original component's functions if it fails, with virtually no interruption of service.
Instantly ready.
Yeah, like a redundant power supply that kicks in instantly.
Mhm.
It's truly seamless for the users. A cold spare, on the other hand, is a duplicate component that is not installed or powered on but is sitting on a shelf, ready to be installed in case of failure.
On the shelf.
Right. Relying on a cold spare, however, results in a period of service interruption while it's being physically retrieved, installed, configured, and brought online. Hot spares are always preferred for mission-critical systems where any downtime, even a few minutes, is unacceptable. Cold spares might be acceptable for less critical components or for situations where physical replacement is feasible without severe business impact, and they're usually cheaper.
The relevance here is undeniable. Anticipating failure through these measures, MTBF, MTTR, redundancy, spares, is absolutely crucial for business continuity and disaster recovery planning. It ensures that critical operations remain functional even when individual components fail.
Which is vital for any organization's bottom line, reputation, and continuous service delivery. This proactive planning is what safeguards against the financial and operational fallout of unexpected outages.
So we've planned for potential failures, building in resilience. But what about the entire journey of a network system, from its very inception, its birth, through its operational life, all the way to its inevitable retirement? That whole lifespan needs managing, right?
Absolutely. That's where network lifecycle management, or NLM, comes in.
NLM, yeah.
NLM is a systematic approach for businesses to oversee every single stage of a network's existence. Its overarching goal is to ensure security, reliability, and readiness to expand with dynamic business needs. It's not just about the network itself, but how it supports and enables the entire organization. It's part of a broader infrastructure lifecycle management strategy that encompasses all IT assets, providing a holistic, long-term view.
So neglecting any stage could cause problems later.
Definitely. Neglecting any stage can lead to accumulated technical debt, security vulnerabilities, performance issues, and missed opportunities for improvement.
Okay. Metering ConnectWise outlines 6 distinct stages for NLM. Let's walk through them, starting with the absolutely critical first step, design and planning. Seems like we keep coming back to planning.
Because it's foundational. The design and planning phase isn't just drawing lines on a blueprint, it's a strategic alignment. This is where you sit down with business stakeholders, not just the IT team, to deeply understand their current and, more importantly, future needs.
Future needs are key.
Critical. Are they expanding into new markets, rolling out a new cloud application, implementing AI or big data analytics? All these factors dictate the network's capacity, its security architecture, its redundancy requirements, and its scalability. A common, costly mistake here is designing only for today's needs without building in the agility and headroom for tomorrow.
Short-sighted.
Exactly. You're essentially forecasting the digital demands of the business for the next 3 to 5 years, identifying critical gaps in your existing infrastructure, and building in security and compliance from the ground up, not as an afterthought. This phase often involves extensive research into new technologies, cost-benefit analyses, and even pilot projects.
Next, we have implementation and deployment, where the plans become physical reality, the build phase.
This is where the plan becomes reality, where the architectural blueprints are brought to life. Hardware is physically installed in racks, cables are run and terminated according to best practices, software is configured on devices like routers and switches, and everything is thoroughly tested to ensure it works exactly as expected and meets all design specifications.
Testing is crucial here.
Absolutely. This phase requires meticulous attention to detail. Pre-configured devices and automation tools like network provisioning scripts can significantly avoid common issues, leading to smoother, faster, and more consistent rollouts. Think about a retail chain deploying Wi-Fi to hundreds of stores. They'd use pre-configured routers and automation to avoid manual, error-prone setup at each site.
Smart. After deployment, we need to keep it running smoothly and efficiently, which brings us to operations and monitoring, the day-to-day.
The goal here is to keep the network running optimally, day in and day out. This means proactively catching problems like sluggish speeds, failing components, or suspicious activity before users even notice, using sophisticated real-time monitoring tools.
Proactive monitoring.
Yes. This phase includes continuous traffic analysis, performance monitoring, routine maintenance tasks, regular firmware updates, and ongoing configuration management to ensure the network remains optimized, secure, and performing according to SLAs. You want to be proactive, not just reactive.
And closely related to operations is maintenance, which sounds like the ongoing care and feeding of the network, keeping it healthy.
Maintenance involves the regular, scheduled upkeep of the network. This includes applying critical security patches to operating systems and applications, updating firmware on network devices to fix bugs and add features, swapping out aging equipment before it fails based on that MTBF data and warranties, and optimizing configurations to meet shifting demands or resolve performance bottlenecks.
Documentation helps here too, I bet.
Oh, thorough documentation and automation of repetitive tasks are lifesavers here, allowing IT teams to focus on higher value activities. Neglecting maintenance is like ignoring the check engine light in your car eventually. Something major and costly will break down.
Then, as the network evolves and business needs change, we move to optimization and scaling, making it better, faster, stronger.
Kinda, yeah. This phase focuses on continuously improving network performance, balancing loads across devices, tweaking configurations for maximum efficiency, and ensuring the network's adaptability to technological shifts or sudden increases in demand. It's about giving your network a performance tune-up and ensuring it remains agile.
Like adding more lanes to the highway.
Exactly. Or implementing quality of service, QoS, for critical applications, upgrading bandwidth on key links, or deploying new technologies. Quarterly audits and performance reviews are key to identifying areas for strategic upgrades to maintain a competitive edge.
Finally, even the best equipment eventually reaches its end. That's decommissioning and renewal, the end of the line.
Right. Even the best equipment has an end of life, EOL, and an end of support, EOS, date from the vendor. This critical final phase involves securely retiring outdated systems. This means careful data wiping and data destruction for storage devices to prevent sensitive information leakage.
Very important.
Crucial. Proper asset decommissioning from inventory systems and environmentally friendly disposal, often through certified recycling programs. Proper planning here ensures a smooth handoff to newer systems and avoids data loss, security breaches, or costly downtime associated with unsupported hardware. And documentation, once again, is critical to track what was removed, why, and how it was disposed of.
There are significant benefits to IT asset lifecycle management that tie all these stages together, right? It's not just busy work.
Not at all. It leads to optimal performance and reliability by proactively addressing issues. It drives cost optimization through strategic planning. It enhances security and risk management. And it provides increased flexibility and scalability. Ultimately, it allows for informed decisions on when and how to plan technology upgrades and replacements, maximizing the value of your technology investments. To manage all of this at scale, especially in complex environments, RMM, or remote monitoring and management, software is a true game changer.
RMM, okay. How does that help?
RMM platforms centralize asset discovery, continuously track the health and performance of devices, automate routine tasks like patching, monitor warranty expirations for renewals, and integrate seamlessly with professional service automation, PSA, tools for service ticket tracking and reporting. It helps manage assets at scale with automation, providing a single pane of glass for everything.
Makes sense. These lifecycle management principles are invaluable, helping students design logical and physical networks, formulate risk assessments, develop security strategies, and configure network devices. This directly prepares students for industry-standard network certification exams by providing that holistic understanding of network operations.
From cradle to grave, essentially.
Exactly. Now, in the fast-paced world of IT, change is the only constant. New software, hardware upgrades, security patches. How do we implement these without causing chaos and bringing down critical systems? This brings us to a crucial, often underestimated discipline: idle change management.
That's a profound point, because the inherent risk in altering any part of a complex system can be catastrophic if not managed properly. So the really important question is, how do organizations efficiently and promptly handle all changes to control their IT infrastructure, minimizing incidents and maintaining current service levels? That's the core objective of change management in the IT service management, or ITSM, context. It's about introducing controlled disruption, not chaos.
So what exactly is ITIL change management, and what are its overarching goals? Define it for us.
ITIL change management provides standardized methods and procedures for handling all changes to IT infrastructure, from a simple software update to a major server migration. Its objectives are multifaceted. Primarily to mitigate risk and impact on services, ensuring changes don't cause new problems, to retain the current working state of the network by having clear baselines, to manage communication and approvals among all relevant stakeholders, to ensure effective change planning using available resources, and ultimately to significantly reduce the number of incidents that occur due to poorly managed, unauthorized, or haphazard changes.
Control the chaos.
Pretty much. It's a framework for deliberate, thoughtful alteration.
Where do these change requests even originate? Who kicks off this process? Is it always IT?
Not always. Change requests can originate from a variety of sources. An incident, like a server crash, might necessitate a change as a fix. A known problem, like a recurring bug, might lead to a change for a permanent solution. An end user might request a change to improve their service. Or, yes, a change manager might initiate one for ongoing maintenance or security enhancements. It's driven by evolving needs from multiple places.
Let's trace the typical change management process flow as described by Freshservice. What's the very first formal step? Someone has an idea. Now what?
The very first step is submitting a request for change, RFC. This is a formal document, a detailed proposal for altering the IT environment. It requires a valid reason for the change, a thorough impact and risk assessment, including which configuration items, CIs, will be affected.
CI is the actual devices or software.
Right. What dependencies exist, a clear cost-benefit analysis, and a detailed implementation plan with proposed timelines, methodology, and required resources. It forces you to think it through.
Once an RFC is submitted, what happens next in the process? Does it just get done?
Oh no, it moves to change evaluation and planning. Here, a change advisory board, CAB, typically a cross-functional committee of IT and business stakeholders, evaluates the RFC.
The CAB. Okay.
Yeah, they might suggest modifications, prioritize the change based on risk, impact, and business value, identify all relevant stakeholders, and meticulously schedule it for a specific maintenance window. This scheduling is crucial to carefully avoid clashes with other major activities or peak business hours.
So the CAB vets it. Then it needs approval.
Yes, change approvals. Clear and timely communication of the change and its details to all relevant stakeholders is key here. The approval process can be manual or automated, with different levels of approval from the CABs, senior management, department heads, depending on the change type and its potential impact. Minor or standard changes might be pre-approved or follow simpler workflows.
Got it. Finally, the change is implemented and then reviewed for its success, right? It's not done until it's reviewed.
Exactly. Once approved, the release management team carries out the actual change implementation following the detailed plan. Following implementation, a crucial change review takes place. This post-implementation review determines its success or failure against the stated objectives, identifies any unforeseen issues, and potentially leads to modifications of the change management process itself.
And the escape hatch.
Crucially, a backout plan is always required and documented before implementation. This plan outlines exactly how to revert the changes if they fail, ensuring you can quickly restore the previous stable state and minimize downtime. It's a critical safety net.
ITIL also categorizes changes into different types based on their impact and risk. Let's look at those, as they dictate how rigorous the process needs to be.
Indeed. These categories are fundamental. Major changes are high-impact, high-risk items, like a data center migration or replacing an ERP system. They require thorough CAB and business approval, have significant implications, and are meticulously planned. Then there are standard changes. These are generally pre-approved, low impact, low risk, happen periodically, and follow a standard procedure like OS patches or new user accounts. They can be templated and don't always need individual CAB approval. Speeds things up.
Makes sense for routine stuff.
Minor changes are normal changes, less risky than major, but don't happen frequently enough to be standard. They go through most stages, including CAB approval, but maybe with less fuss, they might eventually become standard. And then we have the critical category of emergency changes. These are unexpected interruptions needing urgent fixes, security breaches, server outages. These bypass the usual norm, with retrospective RFCs submitted after implementation, and approvals managed by an emergency CAB. Quick resolution is prioritized, followed by documentation.
Got it. So how does this apply in real-world scenarios? What are some practical use cases for ITIL change management that listeners might encounter?
Several key use cases. Business continuity planning, BCP, disaster recovery, DR, often involves major changes for testing or implementation. Fixing security threats is a typical emergency change, high risk, time sensitive. And in modern environments, cloud change management is often handled as standard changes due to frequent releases, but needs careful planning and testing.
Beyond these, what about specific software and hardware changes that this framework governs, like everyday patches?
Yes, this covers installations of new software, applying patches, corrections, improvements, security fixes, performing major upgrades, new versions, big functionality changes, and executing rollbacks, reverting if a change fails. Each of these is a change that needs control.
This all sounds quite complex, but are there some basic steps for implementing any change that listeners should always keep in mind, regardless of type?
There are, and following them is vital. Key steps include never allowing automatic installations for critical systems, determining necessity, reading vendor docs, testing first in a lab, defining scope, scheduling during off hours, maintenance window, informing stakeholders, always backing up the current config first, preventing user access during the change if needed, following instructions carefully, testing thoroughly after, re-enabling access or rolling back, informing stakeholders of completion, and recording the change in the system.
That last one, recording it, seems easy to forget, but critical.
Absolutely critical for the historical record and future troubleshooting.
And how does change management integrate with the broader IT framework, tying into other critical ITIL modules like that CMDB you mentioned?
It integrates seamlessly. It works with the CMDB Configuration Management Database for accurate asset info. It collaborates with release management for the actual implementation. And it's tied to incident and problem management. Incidents can trigger changes, and changes aim to permanently resolve problems. It's all connected.
So there's no one-size-fits-all approach then for ITIL change management. Each company needs to tailor it.
That's precisely right. There's no single universal approach. Businesses must define processes based on their structure, needs, and objectives. The key elements always apply: defining templates, involving stakeholders in the CAB, automating where possible, defining success metrics, and integrating with other ITIL modules.
Right. Understanding change management is crucial for configuring network connections, services, security management, and troubleshooting. It highlights the current and future impact and direction of these technologies and directly prepares students for industry-standard network certification exams by fostering that rigorous, strategic approach to system alterations. It's about being proactive in a dynamic world.
Absolutely. Controlled evolution, not reactive chaos. Hashtag tag tag outro.
What a journey. Wow. Today, we've gone from the very physical foundation of structured cabling, those intricate pathways and organized racks that form the backbone, all the way to the meticulous art of documentation, the network's memory, and finally, the strategic discipline of asset and change management, which dictates how your network lives and evolves.
It's quite a landscape.
It really is a vast landscape of interconnected systems, but every single piece plays a critical, often interdependent role.
We've truly seen how every single component, from a tiny fiber's bend radius to a comprehensively detailed change request document, contributes to the resilience, security, and efficiency of an entire network. Strong connections aren't just about raw speed, they're about foresight, precision and execution, and an unwavering commitment to operational excellence.
Remembering our opening thought that a single tiny bend in a cable or a forgotten software update could bring down systems from the mission-critical cloud to your morning coffee maker, you now understand the complex layers of planning, the robust infrastructure, and the continuous vigilance required to keep those connections alive, robust, and strategically aligned.
Hopefully, yeah. You see the why behind it all.
You are now better equipped to understand the fundamental underpinnings of our truly interconnected world. If you found this deep dive valuable, and we truly hope you did, please like this episode, subscribe to the deep dive, and share it with colleagues or classmates who want to master the backbone of modern tech. It's the kind of knowledge that will give you a real edge.
Please do.
Don't forget, you can find a wealth of additional resources in the description below to continue your learning journey and further position yourself for a bright future. Thank you so much for joining us on the deep dive.
It's been a pleasure to guide you through these essential insights, equipping you for the challenges and opportunities ahead.
Remember, strong connections aren't just technical, they're strategic. Until next time, keep your packets clean and your networks resilient.